Hello. So today I'm gonna go over important topics to know for the Math 114 midterm number 2 or exam number 2, and this class is basically Calculus 3. And the first part is Introduction to Multivariable Functions. The main things to know are how to find and sketch the domain functions, which I have an example here. Just find wherever the function is defined. So here is whenever the thing under the square root is greater than 0, so then you graph it. Finding limit and continuity. First, you can, in some cases, just plug in the numbers and find the limit by direct substitution, but in other cases, you can also prove that the limit does not exist by showing that when you approach the limit from different sides, you do not reach the same limit. So f has two different limits along two different lines, then the given limit does not exist. And other ways to do this is to approach it from x equals y and x equals y squared. And basically in this example, I approached the limit from the x-axis first, so y equals 0, and I plugged it into the original equation and got 1. And for the y-axis, x equals 0, and found the limit, which was 0. So for partial derivatives, the main thing to know is that to find them, you take the derivative with respect to the variable and then treat the other variable as a constant. Variable or variables as constant. And this is the general notation. Another thing to know is that mixed partials are the same. Then the multivariable chain rule, this is the overall equation for it, and some other scenarios depending on where x and y are. There's also some formulas for the implicit differentiation from a multivariable approach. Directional derivatives and gradients. So the rate of change of x in the direction parallel to the x-axis and the rate of change of x in the direction parallel to the y-axis. And the gradient is basically the directional derivative of fxy in the direction of u, which is a arbitrary unit vector at a specific point. And this is the more generic equation. When you're trying to find the rate of change in the direction of an angle with the angle with the positive axis, then you can use u as cosine the angle, sine of the angle, and then this is the equation. To find the maximum value of the directional derivative, that is just the absolute value of the gradient. And similarly, the minimum value is the opposite, and it has the opposite direction. Then here's an equation to find the plane that is tangent to the surface. And here I've explained the generic equation of planes. Now a is the partial derivative with respect to x, and then b with respect to y, and c with respect to z. Tangent planes and differentials. I have the general equation of the tangent line, and this is the equation in standard form, where you are supposed to solve for d. Here's the equation that we saw a few minutes ago. And I've also included the linearization of f at a specific point. And the differential or total differential, and here's the equation. Multivariable optimization, the main thing is to find critical points, and they exist when either both fx equals 0 and y 0, and the gradient equals 0, or where they do not exist. An important note is that not all critical points lead to local maxes or minimums. To determine the nature of a critical point, you're supposed to find the determinant, and this is the equation for it. The determinant is greater than 0, then you check for the second partial derivative of x, and if it's greater than 0, it's a min. If it's less than 0, it's a max. The determinant is less than 0, we have a saddle point, and if it is equal to 0, we don't really have any information. Here are some steps for finding absolute max and mins of continuous functions, finding critical points and evaluating them, finding all extreme values on the boundaries, corner points as well, and evaluate each of these points to find the largest and the smallest, which would be the max and mins. And then Lagrange multiplier method. Basically, it's the equation that summarizes. And to solve problems, you try to set g equals to 0 and set the function that's written here. Then solve gradient f equals 0, partial derivative with respect to x equals 0, with respect to y equals 0, with respect to x equals 0. And then you get the relationship between x and y, preferably in terms of lambda, and then plug these values into the constraint to make a single variable, and find all points that satisfy the equations, and then evaluate f at these points. Two variable integrals basically help you find volume under the graph of the function and above xy plane, and this is the overall equation for what it looks like. Or double integrals over general regions, and order of integration basically tells you which way you're creating these stripes and how it's moving from either left to right or from down to up. And yeah, other factors that also dictate the order of integration are the region or the region and integrand.